Hello. This seems like a really long chapter, I know, but we're almost done with it. This section kind of talks about applications, just different formulas that we can use that involve square roots and things like that. I think you'll see that you've seen maybe one or two of these formulas before, or if you haven't seen it before, you might wonder, why are we just seeing it now? They're not that complicated. I think because a lot of these problems, if you want to solve them, you have to take square roots of both sides of an equation or something like that. And I guess they figure, well, you haven't seen square roots before, but now that you have, it's time to introduce these concepts. So here we are. I have three different formulas we're going to talk about in this section. The distance formula, which they mention here, the midpoint formula, which is fairly simple, and then when they say other applications, really the only application that we're going to talk about is the Pythagorean theorem, which you've seen before, so it's not too exciting of a section, but still good to go over anyway. So just to go over it again, the Pythagorean theorem, remember it only refers to a right triangle. It's not every triangle. It's only a triangle that contains a 90-degree angle, like this guy. 90 degrees here. And if you label the sides A, B, and C, where A and B don't really matter, they're just the shorter sides. It doesn't matter which one's A, which one's B. But C has to be the hypotenuse, which is the longest side. Or if you can't really determine which side is the longest side, like in this picture, it kind of looks like B and C are fairly long. If you can't really tell which one's which, it's also going to be the angle across from the right angle. I'm sorry, the side across from the right angle. There we go. That's probably a better way to remember it, actually. Just look for the right angle or the 90-degree angle and then see which side's across from it. That'll be C. And so anyway, if you have a right triangle with those sides, then there's this property where if you square both of the shorter sides, you add them together, you're going to get the square of the longest side. And usually the application that we'll have, as far as Pythagorean theorem goes, is we'll have a triangle where we know two of the side lengths, like here in example 1, but we don't know the third side length. And we can use the Pythagorean theorem to figure out the last one. So let's try example 1. We have, it says find the missing side length. And really the first thing you want to do is label the sides A, B, and C. Like we said, A and B don't really matter, but the first thing you want to do is identify C. And you can identify C, like we said, by finding the right angle. Here it is. And then figuring out which side is across from the right angle. Looks like it must be the side that has length 13. So I'm going to label that C so I don't forget. But once you label C, the other two sides don't really matter, A and B. So I guess kind of to match the picture, I'm going to say this side is A. They've already labeled it X. I guess they're reminding us that, that's the side we don't know, so we'll call it X. But you can call it A. And then I'll call the side that's length 12 B. But you could switch them. If you made A the side length of 12 and B the side length of X, it wouldn't matter. We're going to get the same answer no matter what. Okay, now that we've labeled things, all we need to do is replace the values that we know into the Pythagorean theorem. Here, let's see, so A we don't know, I guess I'll just replace it with X. Or you could leave it as A, it doesn't matter. But I guess because they labeled it X, I'll replace it. And then B, remember the side length B was 12 here, so I'll replace that guy. And then C, the side length was 13. So I'll replace that as well. And now you can see we have an equation that only has one unknown, X. So we should be able to solve for it. Let me simplify this by squaring the 12. That'll give me 144. And then squaring the 13, that's 169. And then I'll try to isolate X. First thing I want to do would be subtract the 144 to the other side. Try to kind of combine like terms and isolate X. Okay, that'll leave us with X squared equals, what would that be? 25. That's a nice value. Okay. And then we'll finish it off solving it by square rooting both sides. Because, if you want to get X by itself, it's like, okay, I need to get rid of that square, because that's what's preventing X from being by itself. So I say, okay, what's the opposite of a square? Well, it's a square root. And the square root of 25 is 5. So there we have it. It must be that side length X was 5. 5, I guess, if they give us units, like, if these were in feet, they give us one length, the hypotenuse is 13 feet, and then this length is 12 feet. I guess I should put feet here, but there's not really a context or any units that they gave us, so I think we're good to just leave it as 5. All right, but for example, in this second one, they're talking about a wire that's a certain length, and then this pole is 15 feet tall and all that kind of thing. So since this actually has a context, in the end, I'll probably want to write a full sentence to describe my answer. And then also mention the units, of course. Let's see, this example says, how long is a wire that reaches from the top of a 15-foot pole? All right, this kind of helps me to draw a picture. Let's see, say this is my pole here, and it's 15 feet tall. Okay, I'm going to label that. 15 feet tall, okay, fair enough. And then what else? There's going to be a wire that's connected from the top of the pole to a point on the ground that's 10 feet from the pole. Okay, so let's say, here's the point that I'm looking at. That means that the distance from the pole to this point is 10 feet long. And I guess there's a wire that's going from that point all the way to the top of the pole. And of course, since this is coming right after a Pythagorean theorem introduction, it makes sense that this is going to create a right triangle. Okay, looks good. So I think this is going to be similar to example 1. It's just that this time, notice the angle across from the 90-degree angle is the hypotenuse, and that's the thing I don't know. So it's different than example 1 because I did know the hypotenuse and I didn't know one of the other sides. This time I do know the other sides, but I don't know the hypotenuse. So C will be the thing I don't know, and then it doesn't matter. I can label this side A is 10 and B is 15, or you could do it the other way. B is 10 and A is 15, doesn't really matter. But okay, now that I've labeled them, I should be able to just replace them in the Pythagorean theorem here. All right, let's see. A we do know, right? That's 10. So I replace that guy. 10 squared plus B squared, that's 15 squared, equals C squared. Okay. All right, yeah, so far so good. Let's see. Now I need to simplify this. 10 squared is 100. 15 squared is 225. And then C squared, of course, I don't know what C is, so I can't really figure that out. All right, let me add the numbers on the left. 100 and 225 is 325. All right, now I can solve for C. I almost have C by itself. I just need to get rid of that square. And like we saw in the last example, you can get rid of a square by doing the opposite, by square rooting both sides. Because of course we've seen before that a square root and a square cancel each other. So we should just be left with C here. And I don't think 325 has a square root. So we can probably leave it like that, but we probably want to simplify it. We're going to see if there's something that divides into 325 that has a square root. So we should probably simplify that guy if possible. 325 is such a large number, though. I might do like we did in previous sections where we kind of break it down and try to prime factor it. So, okay, 325. What goes into that for sure? I know 5 goes in because it ends in a 5. Let me see, how many times? I have to kind of, I know it's sad to do long division here. Okay, 65 times. Interesting. All right, 5 is prime, but I'm pretty sure 65 is not, right? It ends in a 5 as well, so 5 goes in. Let's see, how many times? 13 times. Okay, sounds good. And 13 is prime, so that'll be about it. All right, looks like, and since it's a square root, remember we want pairs of primes, and I do see one pair of the same prime. There are 2 5s. So let me rewrite this guy. The square root of 325 is the same as the square root of 5 squared times that last prime, 13. All right, and then I can give each of those their own square. Or sorry, give each of those their own square root. Square root of 5 squared, the square root and the square are going to cancel to leave the 5. But the square root of 13, there's not really much you can do with that, so that's about it. Okay, that's as simple as it gets. And let me see if I can put this in a complete sentence, because that's how they like to see word problem answers. What was I trying to look for again? The length of the wire? I think that's what they said. Let me see. After math problems, sometimes I forget what I was doing. How long is a wire that... Okay, yeah. How long is a wire? All right, so I'll just say the wire is 5 square root of 13. And you know what I might do is leave a little space for a decimal approximation, because this is a real life situation. And I imagine if you're, I don't know, someone that works, I guess, engineers and that kind of thing, if you're designing this wire and you tell your boss, oh yeah, I calculated it, and this thing is about 5√3 feet long, how helpful is that? That's not very helpful. You want a decimal probably, right? So I'm going to leave some space. I'll figure out that decimal later. The wire is 5√3 feet long. Okay. Let me see. I'm going to get my calculator out here. Look up the square root of 13. And then whatever that is, multiply it by 5. That's how we'll get this approximation. And I think if there's a problem like this in the homework, they'll tell you where to round. But I'm going to imagine they told us to round to the nearest hundredths. And I got 18.03. All right, that seems a lot more useful, right? I mean, if someone said, oh yeah, that's a long wire. It's 5√13 feet long. It's like, what the heck? What does that even mean? I can't tell if that's long or short. But as soon as I say 18 feet, or a little more than 18 feet, okay, now I can kind of picture that. All right. So hopefully that made sense. It's pretty good. I think we've seen Pythagorean theorem before. So just kind of a reintroduction to it. All right, that's one formula down. We've got 2 more to go, but I think they're kind of getting easier as we go. Although the distance formula is kind of a longer formula. It's not too bad. So okay, the distance formula is talking about the distance between 2 points. So kind of like back in a few chapters back when we were graphing lines and we were plotting points, we could have probably talked about this, but I guess because this formula contains a square root, they didn't want to introduce it until we talked about square roots. So it's the distance between 2 points, as you can kind of see in that picture. They're trying to keep it really general, so they're labeling the 2 points x1, y1, and x2, y2. The distance will be, as the distance formula shows there, it's the square root of parentheses, the difference between the x values, so you subtract them and then you square it, plus the same thing with the y values. The difference between the y values squared. And that's all under a square root. So it's kind of a complicated looking formula, but it's kind of really it's just a matter of plugging things in and simplifying. As long as you're careful, you should be fine. All right, so just keeping that in mind, let's look at these examples here. Example 2, part A. So we have points -7, 4. I'm going to call that guy x1 and y1. So -7 will be x1, 4 will be y1. The other point, 3, -6, I'll call 3x2 and -6, y2. And that way I'll be ready to kind of substitute those in the distance formula. All right, and just to be safe, since this is the first problem we're doing, I might rewrite this guy, just the formula itself, so I have it kind of sitting in front of me. All right, now I'll replace everything I know. But usually what I like to do is just kind of draw the skeleton of it. So I'm going to write all the kind of parts of it without the x2 and y2 and x1, y1. All right, now I'll go ahead and replace them. So x2, what was he again? That was 3. x1 was -7. Let me replace that guy. Got to be careful because there's a subtraction and a negative there. All right, and then we got y2, which was -6. And then subtract y1 is 4. There we go. All right, let me see if I can simplify this here. And of course, here you want to use order of operations. So you want to kind of work with what's in parentheses first, because that's what happened. You know, PEMDAS tells us work with parentheses first. So inside the leftmost parentheses, I have 3 minus -7. That's +10 squared plus, and the same thing in the second parentheses, -6 minus 4. That's -10 squared. Okay, so keep that in mind. Yeah, you want to do PEMDAS. And so since I've already kind of taken care of what's in parentheses, now I want to move on to exponents. I better raise 10 to the second power, that's 100, plus, I'm going to raise this -10 to the second power as well. That'll just be another positive 100, because a negative squared is a positive. All right, we got that, and then moving on to multiplication. There is no multiplication, there is no division, but there is addition. So I'll go ahead and add those guys. 100 plus 100 is 200. And 200 doesn't have a square root, so I can't really come up with an exact answer, but like we saw in the previous example, we can probably try to simplify this guy. Let me see, I'm going to try to break 200 down. 200 is 2 times 100. 100 is 2 times 50. This could be a while, huh? No, it's almost done. 50 is 2 times 25. 25 is 5 times 5. Okay, there we go. Since this is a square root, I'm looking for pairs of the same prime. Here I see 2 of the same prime, and down here I see 2 of the same prime. But there's one odd man out, this 2 all by himself. Let me rewrite this 200 inside the square root as 2 squared, because I had a pair of 2's, and then a 5 squared, because there was a pair of 5's, and then that last 2 that didn't really have a pair to pair up with. So each of those is going to get their own square root, the 2 squared, the 5 squared, and then that 2. For the first 2 square roots, the 2 and the 5 will get to escape the root because they have a square canceling the square root. So it'll be 2 times 5. But this square root of 2 it can't escape, so he'll be stuck there. Looks like it'll be 10 square root of 2, because remember, if you have 2 numbers outside that get to escape the root, you multiply them together. So the 2 times the 5 made the 10. There we go. All right. And that one, probably if this were a real life situation where you want to know the distance between 2 points, it's probably more useful to actually get a decimal. But since there's no context behind it, usually they want a exact answer like this guy, 10 square root of 2. You would not make that a decimal, because as soon as you make it a decimal, you've rounded. You know, you're not giving an exact answer, because this number, 10 square root of 2, would go on forever, the decimals. And as soon as you round, it's not exact anymore. You want to keep it exact unless it's a real life situation. All right, let's try part B. Part B looks kind of scary, mostly because it's a bunch of fractions, right? So that's kind of scary, but it's okay. I think in part B, I don't really need to write the formula again because I already have it kind of sitting next to this problem right here. So I'm just going to kind of copy this down, but like we did before, I'm going to kind of leave the x1, y1, x2, y2 empty. So a distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared, but I'm leaving empty spaces for the x's and y's. I'm going to label these points here. This is x1 and y1. This is x2 and y2. And I'll replace those. So the first spot here is supposed to be x2 according to the formula. That was negative 5/6. And then we're subtracting, let's see, x1, which is this guy, negative 1/2. You got to be careful. The x itself is negative, and there's a subtraction sign in the middle, so be careful there. The next spot is supposed to be y2, according to the formula, but that's 1/6, the way I labeled it, minus y1, which is negative 1/3. So there's another kind of minus, or a subtraction with a negative you got to watch out for. All right. So we'll try to tackle this a similar way to the previous problem. I have to use PEMDAS, or the order of operations. So let's see. I want to add or subtract what's inside the parentheses first. But notice, first of all, though, I think I might go real quick, rewrite what's in parentheses, but where this minus is, or subtracting a negative, I'm going to put a plus, so I don't, kind of makes it look a little simpler, and then I'll be ready for the next step. And same thing with this guy. I got a minus, that'll make a plus. All right, now if I want to add the numbers that are in the parentheses, since they're fractions, they have to have a common denominator. And between the first 2 fractions, the left ones, their common denominator would be 6. So the first fraction's fine. I would just need to multiply the second fraction by 3/3. And actually in the second, while I'm at it, I might as well do the same for the second pair. Their common denominator is also 6, which would mean I'd have to multiply the second fraction by 2/2 to make that denominator a 6. Now let's see how this looks here. The first fraction stayed the same, plus, that'd be 3/6 now, the 1/2 transformed, squared, and then plus, let's see, that was a 1/6. The 1/3 now becomes a 2/6. And we're going to square that. All right, now we're ready to actually add the numbers that are in the parentheses. So in the first one, we have negative 5/6 and 3/6. That makes negative 2/6, because all you're doing is adding their coefficients, or their numerators, sorry. Negative 5 and 3 makes negative 2, plus, same thing in the second one. I add the numerators 2 and 1, you get 3/6. And I'm thinking before I square these, both of those fractions reduce. I think I'm going to reduce them first, because here, negative 2/6, that's the same as negative 1/3, and that's kind of nice. Here we have 3/6, but that's the same as 1/2. That might make it a little easier. We'll see. So now let me square these guys. We have negative 1/3 squared. You can square the 1 and square the 3. 1 squared is 1, 3 squared is 9. And the negative squared will make a positive. Any negative squared is positive. And then on the second fraction, you square the 1, that's a 1. You square the 2, that's a 4. All right, we're almost there. Now I have to get a common denominator so I can add the 1/9 and the 1/4. See, their common denominator would be 36. So I have to multiply the first fraction by 4, so it'll be a 36. And the second fraction by 9, so that his denominator will be 36 as well. And I think we're almost there. Let's see, that'll become 4 over 36 plus 9 over 36. Now they're ready to combine. 4 and 9 makes 13 out of 36. And so this fraction doesn't have a nice square root, but maybe I'll split it into the square root of the numerator and the square root of the denominator. And that way, at least, even though the numerator doesn't have a square root and it can't be simplified, the denominator does, so at least that's something. There we go. That's as good as it gets right there. Alright, so I kind of wanted to go over a complicated one like that where there's fractions, just so you kind of know what to do in that situation. It's just tedious, right? I don't think it's difficult, it's just really tedious and not fun. Alright, we're almost done with this section. That's pretty exciting. So you've put up with the two tougher formulas. This one's a lot easier. There's actually no square roots in this formula, which kind of makes you wonder, why is this formula even in this chapter? Because this chapter is all about roots and radicals. I think just because distance formula and midpoint formula, they're kind of similar. They probably wanted to hold off on midpoint formula since they held off on the distance formula. I guess, that's what I'm guessing. Okay, so the midpoint formula, it's different than the distance formula because, I mean, you look at this picture over here to the right. Here you have 2 points, one on one end here, x2, y2, and you have a second point, x1, y1. Before you wanted to know the distance, so that would be from here to here. Like imagine you get a tape measurer out and you measure the distance from one to the other. That would be the distance formula. But in this formula, we want the midpoint, which is not just a value like 10 feet long or something. We want the actual point that's sitting right in the middle. So the formula is going to produce a point as an answer, not a number as an answer. That's what makes it a little more unique. And it looks like a complicated formula. It's like, you notice there's an x value here, because that's the left portion of this point. And then there's a y portion here. And the way I kind of remember it is, notice the x value of the midpoint, it's like the average of the two x values, x1 and y1. Because, how do you average two things? You add them together and then you divide by 2. And that's exactly what's happening there. You have x1 plus x1 plus x2, and then you divide by 2. So really you're averaging the two x values. And then the same thing with the y value. It's the average of the two y values. So it kind of makes sense that it would give you a point right in the middle. If you average the two x values, that should be an x value right in the middle. If you average the two y values, that should be a y value right in the middle. So this formula shouldn't be too surprising. It's just kind of the average point right in the middle of the two. All right. Let's see. I'm going to just jump into the first example, part A. I'm going to label these guys again, kind of like with the distance formula. Oops, sorry. This is x1, y1. This is x2, y2. Okay. And they want the midpoint. All right, we got midpoint will be, according to the formula, it's x1 plus x2, the two x values averaged over 2. That's the x value of the midpoint. And then the y value is kind of similar. It's the average of the two y values, y1 plus y2 over 2. All right, and then I would just replace the values in there. I'm going to rewrite it with no x and no y. All right, but now I'm going to replace the x's and y's. Here, x1 we labeled as -8 plus x2 is 6. And over here, y1, that was -5 plus y2 is -1. There we go. Okay, looking good. Let's see. So of course, we have a numerator in each case that we want to simplify. On the left one, it's -8 plus 6. That's -2 over 2. And we'll see what that is. In this numerator, you have -5 plus -1. That's -6 over 2. So we'll simplify either of those. Here, -2 over 2, that's going to be -1. Here, -6 over 2 is -3. All right, there we go. That must be the point that's right in the middle of those other 2 points that were given. And if you kind of don't believe it, if you want, you don't have to do this, but it's kind of interesting that way. I'm going to plot the 2 points they gave me. What were they? It was -8, -5. 8. You know, just kind of do a quick sketch. There's 1 point. The other point was 6, -1. 3, 4, 5, 6. There he is. All right, now I'm going to plot the midpoint and see if it looks like it's halfway between. -1, -3. I'd say that looks like about right in the middle, huh? I mean, if it doesn't look like it's right in the middle, it's probably because I drew it wrong. That's kind of interesting, right? So you are really finding the point that's right in the middle of the 2 points given. You don't have to graph it. It's just kind of, if you didn't believe the formula. Sometimes I don't believe it. I say, yeah, right. But all right, let's try part B. It looks kind of scary because there are decimals, but don't worry, not too scary. Probably what we should do first is label these. This is x1 and y1. This is x2 and y2. Okay, so we know the midpoint. The formula is x value is x1 plus x2 over 2. The y value is y1 plus y2 over 2. All right, and if I replace everything I know, it should be just a matter of simplifying from there. I'm not excited about these decimals, but that's okay. The first thing I want to put is x1. That's -3.4. And then next comes x2, that's 4.8. And then here we have y2, but that's, y1, that's 8.1. And then plus y2, which is -8.1. All right. So far, so good. Let me add the numerator here in the left. It's -3.4 and 4.8. That'll be 1.4. And here, 8.1 plus -8.1 is 0. That's kind of interesting. That left one, you have now 1.4 divided by 2. That'll be 0.7. And 0 divided by 2, well, 0 divided by anything is 0. So that must be our midpoint. All right. Well, I guess that does it for this section. We're almost done with this chapter. One more section to go, and then we'll move on to bigger and better things. The last section will be imaginary numbers. So that's kind of interesting. We'll be just playing around and dealing with things that don't even really exist. Isn't that crazy? Sounds fun to me. But all right, thanks for listening, and I'll see you in the next video.